Alright, for next part of this video, we're going to be looking at a test for concavity and something called inflection points, or they sometimes call them points of inflection. So let's do, this is a theorem, and we're going to call this test for concavity. So we're going to assume that f double prime exists for all x that are in A to B. Then we got the following things. If f double prime of x is greater than 0 for all x in that interval. So if the second derivative is positive for all x in the interval, then the original function, say then f, the original function, is concave up. So if the second derivative is positive over an interval, then f is concave up on the interval. And you probably can guess, well, if that happened with the second derivative being positive, if the second derivative is less than 0 for all x in the interval, x elements of A to B, then f is concave down on that interval. Okay. So the next idea, we'll come back and we'll do some we'll do some problems involving this. We're going to combine this with the idea of points of inflection because they're kind of related, or at least when you find one, usually you can kind of get some information about the other. Like in this case, we're going to find the points of inflection, and once we know where those are, we can determine where the second derivatives are positive or negative. So a point of inflection is where a graph changes concavity. So the first thing we're going to do is we're going to kind of try to go through and identify points of inflection, which they also call those inflection points. So let's say we had a graph that looked like this. And we wanted to approximate where the points of inflection are. Or we could say approximate where inflection points are. So what we're going to do is let's label parts of the graph as concave up. So like here we're opening upwards, so we're concave up. You know what, I'm just going to say C up and C down. So C for concave up. So this region of the graph is concave up. This next region is concave down. Over here we're concave up again. And then out here we're concave down. And so what we're going to try to do is we're going to try to approximate the points where we stop being concave up and we start being concave down. So I think the first one is kind of right around here. So we're concave up, we have that kind of parabola opening upwards look through here. And then from here we start becoming concave down. And then here we switch over to concave up. So somewhere probably right about there, the graph stops having this kind of opening downwards shape and starts having this opening upwards shape. And I think if we follow along here, right about here is where we stop opening upwards and we start to get this opening downwards shape. So these red dots that we placed, these would be points of inflection. We're approximating them because I can't tell, like, I don't know exactly where this happens, but you can kind of get the sense from the graph, like, you open up, we stop opening up here, we start opening down, stop opening down, start opening up, stop opening up here, and start opening down for the final bit. So the points of inflection are, if you have the picture of the base graph, you can kind of look at it and tell ballpark where they're going to be, but we really want a way of, like, not just eyeballing it and saying, okay, it's about there. We want a way to figure out, okay, what numbers does it exactly fall on? And so we're going to get a theorem that will tell us how to do that. So this is going to be the test for points of inflection, or we could call them inflection points. So we're going to say for this test, we're going to assume that f double prime exists. And then we say if f double prime at some particular c value equals 0, so if the second derivative equals 0, and f double prime of x changes sign at c, then, so that should be a comma, then the original graph f of x has a point of inflection at x equals c. So basically what this is saying is if your second derivative is 0, and the second derivative flips from positive to negative, or from negative to positive, then you have a point of inflection. Because remember, if the second derivative is positive, then you're concave up. If your second derivative is negative, you're concave down. So we're basically saying if the second derivative is 0 and you change from either concave up to concave down or concave down to concave up at the c value, then that c value is a point of inflection. So we're going to do an example that uses these ideas, and then we'll look at a few more examples. So we're going to say find the points of inflection of f of x equals cosine of x on 0 up to 2 pi. Okay, cosine of x is continuous. Well, actually, it doesn't matter. So, well, we're gonna be able to take the derivative because we're gonna deal with points of inflection, which means we need to take the second derivative, and then it's gonna the second derivative is continuous. Then we're gonna be able to make a couple statements. So, first derivative, if you guys remember, derivative of cosine is negative sine. And then if we have the second derivative, we'll just say, okay, the negative is a constant, so that's going to stay out front. And we take the derivative of sine, which is cosine. So negative cosine of x is continuous, which means negative cosine of x can only switch from positive to negative or negative to positive at zeros. And there's no points where cosine of x is undefined. So basically we know if your second derivative is positive for a while, meaning it's above the x-axis, and then you want it to go negative for a while, you're going to have to cross the x-axis at 0. So what that's going to let us do is we're going to build a chart. First of all, we're going to figure out everywhere cosine of x, negative cosine of x is 0. And then we're going to build a chart with those points. And we'll look at the intervals in between them. And we'll put the second derivative down and figure out if the second derivative is positive or negative there. So let's figure out where is the second derivative equal to 0. So, okay, this just says, well, negative cosine of x equals 0. We have to think back to the unit circle. Cosine of x kind of does the opposite of what negative cosine of x does the opposite of what positive cosine of x does. So negative cosine of x starts out at a, well, let's see. Let's do this slightly different. That'll make it trickier to think about. Let's divide both sides by negative 1. So then this cancels, and we're going to look at 0 equals cosine of x. So basically, where cosine of x is 0, negative cosine of x will be 0 at the same place. And now it's easier to talk about the unit circle without having to like account for the fact there's an extra negative there. So cosine of x starts out here. Remember, cosine of x is the x coordinates on the unit circle. So cosine of x starts out at x coordinate of 1. Up here, it's getting less and less and less, so your x coordinates are getting smaller and smaller and smaller. And then when you're up here at pi over 2, cosine of x is 0, because when you're at pi over 2, you're at 0 on the x-axis. So you started out at 1 on the x-axis, and we went smaller, smaller, smaller till we got to 0. So we'll continue around the unit circle. We're getting bigger, or I guess more and more negative, till eventually we get down here at negative 1. So more negative and negative 1, that's not where cosine of x equals 0. This is where cosine of x is negative. We continue back around. We get less negative. We come back to 0 down here. So at 3 pi over 2 cosine of x is 0. And then we get slightly positive. We're back to kind of small positive numbers. And we build our way back up till we get to x equals 1. So there's two spots where cosine of x equals 0. It's at x equals pi over 2 and at x equals 3 pi over 2. Basically, we're interested when your x value is 0, where are the 2 points from 0 up to 2 pi where that occurs. One of them's here, and the other one's down here. Okay, so I'm going to throw this little unit circle picture. We just kind of use that for scratch work. I'm going to toss that so we get some space to build our table. So what we're going to do with those 2 points is we kind of have this interval. We're starting at 0. We're going to stop up here at 2 pi. We're going to say pi over 2 is about there, and 3 pi over 2 is about here. So we're going to use those to break the second derivative up into intervals. And we're going to build a chart based off of that. So we'll have a 0 up to pi over 2. Whoops, should have put an open bracket on pi over 2. Then we have pi over 2 itself. Then we have pi over 2 up to 3 pi over 2. We got 3 pi over 2. We got the final interval here, 3 pi over 2 up to 2 pi. And we're looking for points of inflection. So we found the places where cosine of x is 0, which means that's the same as where negative cosine of x equals 0, and negative cosine of x is the second derivative. So these 2 points are right here and here. These 2 points are where f double prime of x is 0, because we set the second derivative equal to 0 to calculate them. So if down here represents the second derivative, we know the second derivative is 0 at those 2 particular points. And now this is where we're going to use continuity in order to get that negative cosine of x is positive or negative. Since negative cosine of x is continuous, if it was positive on on one point from 0 up to pi over 2, it's going to be positive for all of them. If negative cosine of x was negative at some point from 0 up to pi over 2, then it's negative for all of them. So let's say, let's look at pi over 3. Cosine of pi over 3 should be a half, but it gets made negative, so we start out with being negative. Between pi over 2 and 3 pi over 2, pi is in between there. So we say cosine of pi is negative 1, but there's an extra negative out front, so it's negative negative 1, so it's positive. So we're positive at a point from that interval. Since cosine is continuous over that interval, we're positive for all the values there, because we know that the only place we can switch from positive to negative is at a 0. So again, this is kind of what I'm saying. If we start out at negative, and we know there's a 0 there, so we were negative at just, I think we said pi over 3. So we're negative here. My function can't go positive and then come back because we found all the zeros. There's only 2 of them. There's not a 0 between pi over 3 and pi over 2. So that's going to force this thing to only cross at the 0. And that's basically how this chart works. Then we say, okay, from 3 pi over 2 up to 2 pi. Let's see, what's in that region? 11 pi over 6 should be in that region. Cosine of 11 pi over 6, let's see. If you remember 11 pi over 6, it's like, here's 2 pi. 11 pi over 6 is the one that's like that. It's sort of the analogous of pi over 6. So it should have the same x value as pi over 6, which is square root of 3 over 2. So cosine of x at 11 pi over 6 is square root of 3 over 2. Square root of 3 over 2 then gets made negative, so we're back to negative again. So to finish this up, we have our table of what the second derivative is doing. It's negative for a while, then it's 0 at pi over 2, then it's positive for a while, then it's back to 0 at 3 pi over 2, then it's negative for a while. So we're going to use our theorem, and we say, well, f double prime of this point here is 0, and there is a change of sign at it, then that means it's a point of inflection. So we'll say both. Again, on the AP test, you can't just say C chart and get your answer. You have to write out how you derived it. So we're going to say both x equals pi over 2 and x equals 3 pi over 2 have second derivative 0 and the second derivative changes sign at them. So they are points. They are inflection points. Inflection points, or we should say, of what function? These are inflection points of the function f, because that's the function whose second derivative we were looking at. So we got our table. We used the table to write the sentence that the AP test is going to want to see. And that's going to wrap up example 2. So we'll look at example 3. This is going to be another kind of in the same vein. And then we'll probably stop part 2 there, and we'll move on to parts 3 and 4. All right, so example 3. What they want us to do is find points of inflection and intervals of concavity. So find points of inflection and intervals of concavity. Okay, so we should say what the function is we're looking at. We're looking at the function f of x equals 3x to the 5th minus 5x to the fourth plus 1. So point of inflection is based where the second derivative is 0 with the change in sign. Intervals of concavity, if you remember from back up here, our test for concavity, if the second derivative is positive, then we're concave up. If the second derivative is negative, then we're concave down. So basically all of points of inflection and intervals of concavity, this is all second derivative stuff. So we're going to figure out where is the second derivative equal to 0, and we're going to build a chart. Okay, there's the zeros. We'll figure out where it's positive and negative. And then if we have zeros with change in signs, where we got points of inflection there. If we have regions where the function is negative or regions where the function is positive, or sorry, the function being the second derivative. So if we have regions where the second derivative is negative or the second derivative is positive, then that will tell us where we're concave up or concave down. So let's look at the first derivative. Let's see, 5 multiplies to 3, that makes a 15. That's 15x to the fourth power minus 4 times 5 is 20. And this will be x to the third power. And the plus 1 just drops. Then we'll look at second derivative. 4 times 15 is 60, so that's 60x cubed minus 3 times 20 is 60x squared. So this right here, this is a cubic. It's not going to be undefined anywhere because we have like no square roots and negatives or no division by 0 or nothing weird there. So we're going to just set it equal to 0, and we're going to figure out what x values make this function 0. Okay, so I need to factor this. So we'll get 60 times x. We'll have x squared. Sorry, 60x squared. Let's remove both x's. That'll leave me a... Well, if I remove 60 and I remove 2 of the x's, that leaves me a single x. Then I remove 60, I remove the x squared, that leaves me a minus 1. So if we look at this function is 0, where if we put a 0 in for x here, so either x is 0, or if I put a 1 in for x here, 1 minus 1 makes that 0. 0 times anything else is 0. So these are my two points that make f double prime 0. So second derivative equals 0 at these 2 points because I took the second derivative, made it 0, and just set the equation equal. So what that means is on my number line here, we have 0, we have 1. We're going to use that to break the number line up into intervals. So we'll have a negative infinity to 0 interval. We'll have 0 itself. We'll have 0 up to 1 interval. We'll have 1 itself. And we'll have 1 up to infinity interval. And we'll look at the second derivative. Again, we're looking for points of inflection and intervals of concavity. Points of inflection are based on change in sign of the second derivative at zeros. We got our zeros here. Second derivative is 0 at 0, and it's 0 at 1. And then intervals of concavity is regions where the second derivative is positive. That will be concave up. And if we have regions where the second derivative is negative, that will be concave down. So let's use a easy to work with number from between negative infinity and 0. So we'll use negative 1. So I'm going to take negative 1, and I'm just going to kind of plug it into this factored form down here to see what the second derivative is. So I'll have 60 times negative 1 squared times negative 1 minus 1. 60 is positive. When you square a negative 1, that's going to be positive. Negative 1 minus another 1 is negative. Positive times negative. The end result is negative. So we're negative over that region. I need something easy to work with between 0 and 1, so I'm going to use 0.5. So I'm going to go to the second derivative. I'm going to use the factored form of the second derivative down here because it's easier for me to think about. You could plug it in up here, but then you actually need to cube the number out and square the number out and see how it works out. This down here we can kind of just get away with looking at the signs since we have three statements multiplied together. So here I'm putting 0.5 in for the x's. So basically what I'm doing is I'm looking at the factored form, and then these two x's, I'm replacing them with numbers from each of these intervals. I used -1 from this interval, I used 0.5 from that interval, and we'll see what goes on here. 60 is positive, 0.5 is positive, 0.5 take away 1, that is negative. So positive times negative says we're negative over this region. So we started out as negative, and then we're still negative. Now I'm going to use an easy to work with value from over here. So between 1 and infinity, let's use 2. So we get 60 times 2 squared times 2 minus 1. 60 is positive. We're multiplying that by 2 squared, which is positive. 2 minus 1 is positive, so it'd be positive times positive times positive. Says our end result there is positive. Okay, so we got what we need. We have one inflection point. We have a point of inflection at x equals 1 as f double prime of x equals 0 and f double prime of x has a change in sign. So at 0, the second derivative was 0 there, but we did not have a change in sign. We started out as negative, and then we came back as negative. So there was no change in sign there, so it didn't create a point of inflection. This one we changed from negative to positive, so we did get a point of inflection out of it. Let me create some more space to write the rest of the answer here. Okay, we're going to get f is concave, we'll write down first, down on negative infinity to 0 and 0 to 1. The reason for that is f double prime of x is less than 0 there. So we'll say, all right, we're concave down on the two intervals where the second derivative was negative. And as you guys probably can guess, we're going to be concave up on that last interval where the second derivative is positive. So we'll say f is concave up on, let's see what the interval was, 1 up to infinity as f double prime was greater than 0 on that interval. Okay, so we answered everything we wanted. We got the point of inflection. That was second derivative is 0 with the change in sign. There was only one of them at x equals 1. This one here at 0 did not create a point of inflection because there was no change in sign. We got concave down on these two intervals where the second derivative was negative. And we got concave up on the one interval where the second derivative was positive. And they asked us for points of inflection and concavity. So we got them all taken care of here. Okay, so we'll stop part 2.